Hi, today we will be looking into the design of flat belt drive. Let us look into the question. Design the flat belt drive with power of 15 kilowatt, life 1800 hours, motor speed 1440 rpm, reduction ratio is 1.8, thickness of the belt 5 mm and service factor is 1.25. Let us start with the design power. Since they have given us the service factor, the design power turns out to be as 18.75 kilowatt. Since we know the reduction ratio and the motor speed, the machine speed becomes 800 rpm. It is important to observe that in this particular question, the application of this particular flat belt drive is not mentioned. So that's why I used a word called machine speed. Let us look into the figure. The smaller circle is known as motor pulley and the bigger circle is known as machine pulley. The distance between the center to center distance between the motor pulley and the machine pulley is C. The diameter of the smaller pulley is represented by small d and the diameter of the bigger pulley is represented by capital D. You can see here that there is an angle called theta 1 and theta 2. You can also observe there is a symbol called as alpha, and alpha makes an angle. It is important to observe that the belt makes contact with the pulley alpha degree ahead of the vertical line. In the same manner, for the smaller pulley, the belt makes the contact with the smaller pulley with alpha degree later to the vertical line. Hence, when I would say what is theta 1, I can say that theta 1 is 180 degree minus 2 alpha. Similarly, I can say that what is theta 2? Theta 2 is 180 degree plus 2 alpha. So we can see that the smaller pulley makes less contact with the belt, whereas the bigger pulley makes more contact with the belt, and this particular terminology is called as arc of contact. The arc of contact is more for the bigger pulley, not only because of the diameter, as the diameter is big, but also because of the alpha degrees or alpha angle. We have seen the terminologies here where T1 and T2 are tight side and slack side of the belt. We'll start with calculating the smaller diameter, and the smaller diameter is calculated by the Severin equation. This particular formula is not there in the PhD design data book. We say that 1100 and cubed under root PD by N1, and this is to the left side, and to the right side we have 1300 cubed under root PD by N2. We know what is PD, design power, and N1 and N2 are known. Hence we can come up to this value called 258.7 and 37.2. So this is the range of the minimum diameter of the smaller pulley. So your smaller pulley diameter should be in between those values. Either it should be 258 or maximum it can be 372. But as we know, we have a habit of selecting standard diameters of the pulley. So from page number 7.54, the standard diameter is 280 mm. Now, once we have selected the standard diameter, we are interested to find out the diameter of the bigger pulley, that is D. Now, capital D is given by this formula, and this formula appears in page number 7.61. Eta is something I would assume. and that is the efficiency of the power transmission, and I can say that it is 0.98% efficient. When I substitute the values, the value of D comes around 493 mm, and a standard dimension from page number 7.54, it comes around D is equal to 500 mm. Now you can observe that I have written here arm type and web type. So the rule is, once your diameter is more than 300 mm, you can say you can use arm type of pulley, and once your diameter is less than 300 mm, you can say web type pulley. Now the similar concept we also use in the gear design, whereas we have arm type of gear and web type of gear, and that also holds this 300 benchmark. If 300 is more, the value is more than 300, we can say it is arm type, or if it is less, we can come to conclusion that it is web type. Now we know this table, that pulleys can be made of cast iron or it can be made of mild steel. There is one more part in point B, that is mild steel spokes. Now these spokes, instead of arms, they may have spokes similar to your bicycle wheel. So neither it is web type, but it's a type of thin rod that is connected to the hub, to the rim. Now generally I know that the cost of cast iron pulley is quite less, easy to manufacture, the wastage of material is also less. That's why I'll be selecting cast iron type of pulley. In cast iron type of pulley, there are two types: solid with flat or crown face, or split with flat or crown face. Now if your value of maximum rim speed or maximum speed of the belt, or is the same, the pulley speed is between 1000 to 1500 meters per minute, if it is within that range, you can select solid with flat face. Or if your pulley, if your value of maximum rim speed lies somewhere 1 meter per minute to 1000 meters per minute, anywhere in between that, you can select split with flat face. So once we have selected the type, depending upon your speed of the pulley, we can come to conclusion which one to select. Moving ahead, we will calculate the speed of the belt, and the speed of the pulley is the same. So pi dn, and we know the diameter of the smaller pulley, and we know the speed by which the smaller pulley is rotating. The value comes around 1266.69. okay, so this particular value 1266.69 it lies between 1000 meters per minute to 1500 meters per minute. Hence I can say that we can select a solid type of face. Now when you take it in terms of meter per second, that it comes around 21.11. Now this value 21.11 is really very high, so we should understand that the belt is rotating with pretty high velocity. Now once this is over, we have selected the type, that is cast iron, and the subtype like solid face or split face. We have selected one of that. We will try to calculate what is the center distance. The center distance is represented by the symbol called as C. Now C is 2 times diameter, that is the bigger diameter, so the value comes around 1000 mm. Once this is done, we will calculate the total length of the belt. Now before we calculate the total length of the belt, we have to select the configuration of the belt. The belt can be open drive, cross drive, quarter drive, and the formulas related to this appears in page number 7.53. For simplification, we will select open drive, and the total length of the belt is represented by L, and the length of open drive is given by this particular formula, which is present in page number 7.53. We'll substitute the values which are known to us, and the length comes around 3237.32 mm. Once this is done, we will calculate the angle of lap. Angle of lap, as we had seen from the figure, theta 2 is equal to 180 plus 2 alpha, theta 1 is equal to 180 minus 2 alpha. We can also see from the figure sin alpha is equal to d capital D minus small d by 2c. So since we know this particular parameters, alpha can be calculated, and it comes around 6.315 degrees. Now theta 2, as we know, would be bigger, that is 192.63, and theta 1 comes little smaller to it, that is 167.37 degrees. We will select the belt material for our drive. Dunlop high speed belt with nominal weight 878 grams per meter square. It has soft fabric. There are two types of fabric which are available. One is called as soft fabric and the other is hard fabric. So if we will try with soft fabric, so if it can take up the load, then our selection would be correct. The next point is the properties of this particular belt material. These properties are not given in the design data book and can be taken from the manufacturer's catalog. Rubber canvas being the material, the ultimate tensile strength is 45 Newton per mm square. The Young's modulus is 100 Newton per mm square. The coefficient of friction is 0.25 and the density is 1200 kg per meter cube. In this particular problem, we can identify which is the smaller and the weaker pulley. As we know, theta 1 mu is lesser than theta 2 mu. According to calculations, we can come to conclusion that the smaller pulley is weaker and the bigger pulley is comparatively strong. Now, once we have come to conclusions that the smaller pulley is weaker, we will focus on that and we will try to design the smaller pulley in the first case. Now T1 and T2 are the tension in the tight side and the slack side of the belt. We know this equation and we can substitute the values of mu and theta 1, and the ratio T1 by T2 comes as 2.075. To calculate T1 and T2, we require the torque equation. In the torque equation, we need to know what is the torque. Torque can be found out from the power equation. The power is 2 pi nt by 60. By substituting the values, the torque comes around 124.33 Newton meter. If you multiply it by 10 raised to 3, it comes around 124 into 33 into 10 raised to 3 Newton mm. Now, after considering equation number 1 and equation number 2, we know that there are two unknowns, and since there are two equations, we can find out what is T1 and what is T2. Now, the T1 is 1713.55 and T2 is 826 Newton. Since T1 is quite higher, we will say that T1 is equal to T max. Now, we'll calculate the stress cycles. To calculate the stress cycle, which is represented by eta b, we need some parameters. Life of the belt is something given in the question, which is expected to be 1800 hours. V is known to us, length we have calculated. Eta p means the number of pulleys along the drive, and we have selected two pulleys. One is the driven pulley, the other is the driver pulley. Since there are only two pulleys, I will write that value as 2. When I substitute the values, my eta b stress cycle comes around 84.50 3 into 10 raised to 6 cycles. Once we have done that, we can calculate the maximum tensile stress based on endurance limit. Now this is the formula you may have seen in the fluctuating stresses. M is a factor which is phi for the flat belt. Eta B is something we have just calculated, that is the stress cycles. Sigma minus 1, that is the nominal stress, is equal to 0.2 sigma ut. We know the sigma ut from the material properties. Hence, substituting those values will help me to find out sigma T max, which comes around 5.8730 Newton per mm square. The induced maximum tensile force in the belt, sigma T max, can be divided into three parts: the tensile stress, centrifugal stress and bending stress. Each of which we can substitute and try to find out the parameters. Sigma T is T max by area. We know the area of the rectangular flat belt, that is B into T, and thickness is given in the question where T is equal to 5. Sigma C is rho V square. Now rho we already know and velocity is already known. So sigma C, that is centrifugal stress, can be 0.534 Newton per mm square. Sigma B, that is the bending stress, can be found out by the flexural formula, and substituting Y, that is from the center to the outermost fiber, and R, that is the radius of the pulley, and E, that is the Young's modulus, sigma B can be calculated. It comes around 1.7857 Newton per mm square. Once we know both the formulas, that is induced maximum tensile stress due to endurance limit and due to induced stress in the belt, I can put up this equation and write the substituted values. B is an unknown factor, and when calculated it comes around 96.25 mm. Once B is known, we need to calculate parameters that are associated with width of the belt, which is represented by B. Now the parameter that is represented by B is called as I, that is plies of belt. So B and I are important factors that we need to state while we select a belt from the vendor. Now the formula millimeter plies of belt appears in PSG 7.54, and you will get the value of B into I if you divide the corrected load by the load rating per mm per kg at belt speed. We will calculate what is corrected load. The formula for corrected load is there in page number 7.54. Corrected load is equal to load on belt service factor multiplied by arc load correction factor. When we look onto these parameters, we can say load on the belt is known to us, that is 15 kilowatt. Service factor is also known. We need to find out what is arc load correction factor. Arc load correction factor depends upon the parameter called arc of contact. Since we know the arc of contact by this formula, which is there in 7.54, we can substitute the values, and the arc of contact comes around 166.8 degrees. We can round it off to 170 degree. Now when you look into the table which appears in PSG 7.54, we can say that the arc of contact is connected with the arc load correction factor, and from the table we can say that for 170 degree for arc of contact, the arc load correction factor is 1.04. Now we know the parameters that are connected with corrected load. We can substitute them and it comes around 19.5 Newton. We need to calculate one more parameter that is called as load rating at 21.11 meters per second speed. So that is the speed for our belt drive. Now this formula is equal to load rate at 10 meters per second multiplied by V by 10. The load rate at 10 meters per second is given in the design data book, which comes around 0.023 kilowatt. We know the velocity of our belt drive. By substituting the load rate at 10 meters per second and then multiplying it by the speed by 10, what we get is load rating for 21.11 meters per second, that is 0.048 kilowatt. Now we can substitute both the parameters in the main formula, that is millimeter plies of belt, and when we put it up together it comes around 406.25. B into I is 406.25. Now we know this equation and we have calculated the value of B, but we know I is known as number of plies. So when I is equal to 3, B is 135.41 when we substitute in this equation. When I is equal to 4, when we put in this particular equation, it turns out to be 101.56. When I is equal to 5, when substituted in this equation, the B value comes around 80.4, and so on. Now I are the standard values like 3, 4, 5 and so on, but this particular B, they are not standard values. So we will go to PSG 7.52 and try to identify the standard value, and you can observe that only a value close to 101.56 is available. So the value close to 101.56 is 112. Now when you multiply 4 with 112, you get 448. 448 is a bigger number with respect to 406.25, but 448 also indicates it is much safer than the 406.25 value. So we can select I is equal to 4 and B is equal to 112 with confidence, and the system will become more safer. This particular value of standard B is available in page number 7.52. By this point we have finished the flat belt design.